In this lecture, we will be talking about the echelon form and the Gauss and the Gauss-Jordan elimination. But first, let's talk about what we mean by leading coefficients in a matrix. So you look at the matrix, you look at a particular row of the matrix, and you find the first non-zero coefficient going from left to right. That coefficient is called the leading coefficient or the pivot of that particular row. If every element in a row is 0, then we call it a zero row, and in such a case it has no pivot. And here is an example. All the pivots or leading coefficients are in red. In the first row, the pivot is in column 1 and it's equal to 1. The second row, the pivot is in column 2 and equal to 3, and so on. And the last fourth row has no leading coefficient. Moving on to row echelon form. So let A be just any n by m matrix. It does not have to be a square. In that case, we say that this matrix is in row echelon form if the following two conditions are satisfied. First, if A has 0 rows where all elements are 0, they must all be at the bottom of the matrix. Second, if a particular row, let's say row I, has a leading coefficient in, let's say, column J, then if you move to the row just below that one, I plus 1, then the leading coefficient of that row must be strictly to the right of the leading coefficient above it. That is, it must be in column J plus 1 or higher. So here's an example of a matrix in row echelon form. So let's look at the matrix A to the left. First, we see that it has 1 0 row and it's at the bottom. So the first condition is satisfied. To check the second condition, highlight all the leading coefficients and make sure that as you go from row 1 to row 2 to row 3 and so on down the rows, the leading coefficient of the following row must be at least one step to the right of the leading coefficient above it. So the first matrix is okay. The first row has a leading coefficient in column 1. Moving down to the second row, the leading coefficient is one step to the right in column 2. Moving to the third row, the leading coefficient is in column 4, which is 2 steps to the right of the one in row 2, but that's okay. One step or more. And the fourth row has no leading coefficients, so that's okay. The matrix A to the right fails to be in row echelon form because of the leading coefficient in row 3. That's in column 2, which is the same column as the leading coefficient in row 2, the number 3. And that's not allowed if the matrix is to be in row echelon form. If you have a matrix in row echelon form, we often draw the following lines to outline the position of the leading coefficients. We do the lines like this, and the lines are drawn such that each leading coefficient is at a corner of these lines. In some cases, this outline is what's important and not the actual numbers themselves. And so you might see something like this, where all we care about is where the leading coefficients are. In this example, we recognize that they are here, 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 and here. So there are leading coefficients in column 1, 3, 4, and 5. With an outline like this, all the elements to the left of this outline must be zeros. There is another form of a matrix which is also important, and that's called the reduced row echelon form. The conditions for a matrix to be in reduced row echelon forms are as follows. 3 of them. First of all, it must be in row echelon form. Second, every leading coefficient must be 1. Remember, the leading coefficient was the first non-zero element of a row. And finally, if there is a leading coefficient in column J, then that can be the only non-zero element of that column. Keep in mind that this does not mean that a column can have only one non-zero element, because it might be that there is no leading coefficient in a particular column, and in that case there can be many elements which are non-zero. So here first is an example which is in row echelon form but not reduced row echelon form. The leading coefficient of the second row is directly to the right of the leading coefficient of the first. The second condition of a reduced row echelon form is satisfied as well. Both of the leading coefficients are equal to 1. And I should mention that some authors do require the leading coefficients to be equal to 1 for a matrix to be in row echelon form. But the final condition is not satisfied. For the first column it is. There is a leading coefficient in 1, 1, and that's the only non-zero element of column 1. For column 2 it's not. In column 2 there is a leading coefficient in 2, 2, but it's not the only non-zero element of that column because there is a 2 in 1, 2. And so here is an example of a matrix which is in reduced row echelon form. We now have a 0 in position 1, 2, making the leading coefficient in the second row the only non-zero element of the second column. If you look at the third column, there are actually 2 elements which are non-zero, but that's okay because there is no leading coefficient in that column. So now on for the important question of this lecture. Is it possible to start with any matrix and by performing elementary row operations on that matrix, transforming it into row echelon form? And or is it possible to transform it into reduced row echelon form? The answer to both these questions turn out to be yes. And the procedure for actually doing it is so important that they have names. Transforming it into row echelon form is called Gaussian elimination, and transforming it into reduced row echelon form is called Gauss-Jordan elimination. So let's begin by considering Gaussian elimination. The main result is that you can start with any n by k matrix and transform it into a row echelon form using only elementary row operations. That is, you can swap rows, you can scale rows, and you can add a multiple of one row to another. We are not going to prove this, but simply outline the idea. This is a case where it's actually more useful if you convince yourself that you can transform any matrix into row echelon form by doing a couple of examples and perhaps trying to come up with a matrix which cannot be transformed into row echelon form and convincing yourself that such a matrix doesn't exist. But the basic idea is this. First, we can use the elementary row operation 1, that is the swapping rows, to put all the 0 rows at the bottom. Then just go column by column. Let's say first of all that this one here at 1, 1 is not 0. Well, in that case you can use the third operation to turn all these guys into 0. Next, let's say that this guy is not 0. Again, use the third to make these into 0. Then you can do the same for the third column, assuming that this is not 0. You can make this into 0, and then you're done. In this case, the outline became like this. There are a couple of things that can go wrong with this simple strategy. First, if you have a 0 in 1, 1, well, in that case, I can't use the first row to eliminate the rest of the elements in the first column. All I have to do in such a case is to find a row with a non-zero element in column 1. So let's say, for example, that this is non-zero. Well, then all I do is I swap these two rows and then I'm back to the previous case. If there are no non-zero elements in the first column, then that's okay. Just move on to the second column. Another interesting thing that may happen is the following. Say that you have a leading coefficient in 1, 1, and you have eliminated all the other elements in column 1. Then, moving on to column 2, the goal is to position a leading coefficient in position 2, 2. If 2, 2 happen to be 0, you can look at 3, 2 or 4, 2 and check if that's non-zero. If any of these two are non-zero, just swap these rows so that you get a non-zero element in 2, 2. But it actually may happen that all these three elements are 0. And in that case, it's not possible to get a leading coefficient in position 2, 2. Well, no problem. Just move on to the third column, like this. Then, perhaps you can find a leading coefficient in row 2. And perhaps also one in row 3, and we get the following outline. But again, the best way to convince yourself that you can always do this is to do a couple of exercises. So the basic idea with Gaussian elimination is that you start with an arbitrary matrix A. You perform elementary row operations on this matrix. For example, in the first step, you make element 2, 1 into 0. In the second step, you make element 3, 1 into 0. And then you keep on going like this until you finally end up with a matrix in row echelon form. But since every step is an elementary row operation, every matrix in this diagram are row equivalent, including the first and the final one, which is in row echelon form. So A and B must be row equivalent. That is, another way of saying that any matrix can be turned into row echelon form is that for any matrix A, there exists a matrix B, which is in row echelon form and is row equivalent to A. We should also note that B is not unique. That is, for a particular matrix A, there are many row equivalent matrices B in row echelon form. For example, let's say I start with the matrix A. I perform elementary row operations until I get to B, which is in row echelon form. In this case, if I add the second row to the first, I get 1, 1, 3, 0, 1, 1. But this is also in row echelon form and it's row equivalent to A. So B prime is the second example of a matrix in row echelon form which is row equivalent to A, and there are an infinite number of such matrices. The procedure just described, that is what's called Gaussian elimination. If we want to extend the elimination so that we get to the reduced row echelon form, as mentioned previously, then we typically call it the Gauss-Jordan elimination. And so any matrix can be transformed into a matrix in reduced row echelon form. But in this case, the matrix is unique. For a given matrix A, there is one and only one matrix B, which is in reduced row echelon form and which is row equivalent to A. The procedure to go to the reduced row echelon form is quite similar. So you start with any matrix A. First, you make it into a row echelon form, for example, like this. Once you have it in row echelon form, you can use the second row to eliminate that one using the pivot operation. And you can use the third row to eliminate these two. So you can keep on going until you have this result. And the final step is then just to use the scale operator to make this into 1 and these two into 1. Here is an example. First, get rid of the element in 2, 1 by adding the first row to the second. That takes care of the first column. Then remove the 1 in position 3, 2 by adding -1/2 times the second row to the third. Like this. Now it is in row echelon form with the following structure. But it's not in reduced row echelon form because the leading coefficient in row 2, the number 2, it's not the only non-zero element of its column. So the next step is we have to eliminate this one here. That we can do by adding -1/2 times the second row to the first, which will give us this matrix. And then there's just one step left, and that's to scale the second row by 1/2 such that its leading coefficient becomes 1. And now the matrix is in reduced row echelon form. Why is it unique? Well, this final matrix B is in reduced row echelon form and is row equivalent to A. But you should convince yourself that if you perform any elementary row operation on B, it will no longer be in reduced row echelon form. I can't swap any rows, I can't scale any of the rows because that will make the leading coefficient not being equal to 1. And I can't add a multiple of one row to another without destroying the reduced row echelon form. And the procedure just outlined going from A to B is then called a Gauss-Jordan elimination. Since you can identify a clear strategy for transforming a matrix into reduced row echelon form, you can program it. There is no function in the standard packages of R that will transform a matrix into reduced row echelon form. But if you download the package JLA, there is a function called RREF, reduced row echelon form of A. Here is the matrix that we consider for our example. And here is the matrix in R. To get this into reduced row echelon form, you simply type this, and you can see the answer here is the same as what we came up with. This function also returns LCC, which is leading coefficient columns 1 and 2. So LCC will contain the column numbers where there are leading coefficients. This function actually returns what's called a list, and if you need to work with the reduced row echelon form, you can put the list in B, and then you refer to the reduced row echelon form by B $RREF like this. Finally, a couple of important results on the reduced row echelon form. First one, two matrices will be row equivalent if and only if they have exactly the same reduced row echelon form. Proof will be in an exercise. This result is really useful if you want to determine if two matrices are row equivalent. All you have to do is to put both of them into reduced row echelon form and compare the results. If they're the same, they're row equivalent. If they're different, they're not. The identity matrix is in reduced row echelon form, as you can convince yourself, which is to say that the reduced row echelon form of I is I itself. Combining these two results, we have the most important result, which is a matrix is invertible if and only if its reduced row echelon form is the identity matrix. Remember, we previously had a result which said that a matrix is invertible if and only if it's row equivalent to the identity matrix. Well, the first bullet says that A and I are row equivalent if and only if they have the same reduced row echelon form. And since the reduced row echelon form of I is I, A is invertible if and only if its reduced row echelon form is I. Returning to this example A, we found that the reduced row echelon form was this, which is not the identity matrix. That means that A cannot be invertible. We can easily check that by doing solve A, and it's confirmed. Let's consider another matrix B, which is 4 by 4, and let's find its reduced row echelon form. We see that the reduced row echelon form is precisely the identity matrix, so we know that B must be invertible. How to find the inverse will be discussed in the next lecture, but let's just double check that it actually is invertible, and it is with this inverse.